This kind of an image is not new to us, especially for people who love forensic science. But what exactly is this? It's an image of the separated DNA fragments on a piece of gel. And the process of separating them is called gel electrophoresis. Doesn't this sound very difficult? Separating DNA fragments on a piece of gel? But actually, the process of gel electrophoresis is not very difficult. In fact, it's quite easy. Let's have a look at how the process works and also the principle behind it. Let's begin with the definition first. Gel electrophoresis is a technique to separate the different DNA molecules based on their sizes. Can you guess why is it called gel electrophoresis? Okay, let me help you with this. This separation technique is based on the movement of charged molecules when exposed to an electrical field. And this movement occurs in a gel medium. Hence, it's known as gel electrophoresis. Now let's understand the process step by step. But before that, since the term charge is used by us here, can you guess the charge present on a DNA molecule? Let me tell you that a DNA is negatively charged. And this is due to the presence of phosphate groups. These phosphate being negatively charged and present in the backbone of the DNA double helix impart a negative charge to the complete molecule. And what is the gel used? Interestingly, the gel which is generally used for the DNA is agarose gel, and it's obtained from the seaweeds. Now getting back to our process. We said that the DNA molecules get separated on the basis of their sizes. So if we have a sample of DNA which is containing fragments formed with the activity of restriction enzymes, then separating the fragments based on the difference in their sizes would be possible with gel electrophoresis. Let's have a look at this in detail. To understand the principle and working, let's take the analogy of a sieve. We know that if a mixture of different sized particles is poured onto a sieve, then only the particles smaller in size than the pores will escape, while those bigger in size will be retained back. Here, the size of the particles is the only parameter used for the separation. Same is the case with DNA fragments. When our DNA sample containing various size fragments is loaded onto a gel, then the charge applied across the gel helps in the mobility of these fragments. However, not all fragments move at the same pace. Those which are smaller move ahead, and those which are larger in size find it difficult to move. To understand this better, let's zoom into the gel that is prepared for the experiment. Here, at the microscopic level, we find that the gel appears to be a mesh-like structure and the pore size is nearly constant throughout. So now imagine what will happen if different sized DNA fragments are made to pass through these pores. It's obvious that the small size fragments will escape the pores faster, while the larger fragments will find it difficult to come out. They will take a lot of time to cross the smaller pores and thus will lag behind. This is how we can understand the principle of separation of the DNA fragments based on their sizes. Now let's see how the procedure works. The first requirement is the complete setup. This will include the casting tray, gel, a comb for making wells in the gel, electric supply, and most importantly, DNA sample with different sized DNA fragments. Here's an illustration of the casting tray containing the gel in which we will load the DNA mixture. We usually opt for a comb to form well-like structures into the gel. And why do we do that? Because it's in these wells in the agarose gel that we load the DNA mixture. Now tell me, where should the wells be formed? At the ends or at the center? Think about it. We know that the DNA fragments, being negatively charged, will travel from a point of negative charge to the point of positive charge. Thus, we need to form the wells to load the DNA samples near the negative terminal, or the cathode to be precise, so that the DNA will move towards the positively charged anode. This movement of the DNA molecule will be promoted by the electric field. But we cannot track the movement of the DNA in the gel as it's colorless. For this, we use a colored loading dye to track the movement of the DNA. The mixture of the DNA samples with the colored loading dye is now all set to get into the gel. But before loading the DNA mixture, we will fill the apparatus with a buffer as shown. The buffer is used to provide better conductivity of electricity. Next, we will load the DNA mixture into the wells and we are ready to turn on the power supply. Once the power supply is turned on, the DNA mixture will move through the gel, which can be tracked with the help of the loading dye. The loading dye is selected in such a way that it travels a bit faster than the DNA segments present in the mixture. And why is that so? That's because we want the loading dye to reach the terminal end faster than the DNA. Once the dye reaches the anode, we get an indication that the DNA must have reached somewhere near, and thus the power supply has to be turned off. Moving ahead with the next step now. We know that the DNA molecules have got separated. But can we really see them? No, that's not possible. So how will that be possible now? How do we observe the separated segments? To observe the DNA molecules, we treat the agarose gel with ethidium bromide solution. The major reason for using ethidium bromide is that it easily binds to the DNA molecules, and when the agarose gel containing the DNA is observed under ultraviolet light, bright orange-colored bands are clearly seen. These are nothing but the bands of the DNA. The separation has been successful based on the size of the DNA fragments. The larger molecule are the ones found here, which means these are the ones that moved slowly. On the other hand, the smaller molecules which moved faster are the ones spotted here. Now, how do we know the size of any DNA fragment? The bands obtained are compared with a standard chart known as the DNA ladders. On comparing the positions of the bands with the ones from the chart, we can easily make out the length of the fragments obtained. Once we know the lengths of the fragments, we can easily identify the desired DNA. Now, the desired DNA fragment can be first manually cut out from the agarose gel and then extracted. This process is called elution. The extraction of the DNA is done in such a way that it can be used for further downstream processing. This was the simple explanation of how any gel electrophoresis technique works. It's considered as one of the very important techniques used in recombinant DNA technology. To learn more about such interesting processes, stay tuned to our channel and do not forget to subscribe. Happy learning!